Hello, everyone, and welcome. Tonight is our DS Code Pudding. My name is Tiffany Hall. I am an alumni of TripleTen Software Engineering Program, and I want to thank you guys so much for joining tonight. I am a full stack engineer, but tonight is my favorite gig, which is that I get to do all of the hosting and see all of the wonderful projects our students have come up with. So, if you are not familiar with what a code pudding is, let me take a moment to just kind of acquaint you with our fun games. Our code puddings are a very short competition here at TripleTen, a friendly competition, though, of course, no bloodbaths allowed. Our friendly competition is very short. We're talking 5 days or less, where our students are competing during their normal coursework, too. We give them a prompt and then they are putting in the work together. Ashok, these are the jokes, man. You got to laugh at them. These put in the work together to get um, all of our finer points met in our brief. And then our judges will meet next week and evaluate. So our code pudding consists of two parts. We have working with the data and building the model with the presentation. So we had the data and building the model occur in the past 5 days, and tonight we get our presentation part. You might be wondering what the prompt was this month. Our prompt this month was um, keeping up with our music and exploration. Music's been very hot this week. I don't know if anyone else saw the big release. I did, of course, because I'm a big old Swiftie. But the rest of our students, whether they are or aren't, are exploring Spotify even more and building models in a new way. So last week, they have been divided into teams and been challenged to build a model that can predict Spotify's popularity metric of a song using a pytorch neural network, which sounds really impressive, even if you know nothing more, but they're going to tell us lots more about it. We're going to explore different aspects of neural networks as an attempt to get the best model possible. So, very exciting. I'm so glad you are joining us. The judges will evaluate next week for the model and the presentation. All of the results will be posted on the Hub and socials on August 27th. And then if you're watching at home or watching this on replay, if you're a student of ours at TripleTen, you can go ahead and vote for your favorite team on the Hub. If you're not a student of ours just yet, you can either vote in the live chat, because this is a live broadcast, or you can watch it on replay later and vote in the comment section. To vote for your favorite team, all you have to do is type in the name of your team vote. Pretty simple. All right, let's go ahead and get cracking. My favorite part is not the part where I do the talking, it's the part where I get to see all the fun presentations and show them to you. All right, so our first group tonight, we have three teams. The first team is Torch Quest, and that team consists of Gil Fadu, Preeti Sagar, Ashok Mahajan, and William Mazzeo. I got him. All right, Torch Quest, it's your turn.
Okay, hi everyone. Have you ever wondered what makes a song go viral? Is it the beat, the energy, or something hidden in the audio features? To explore the question, our team Torch Quest worked on this project to build a model to predict song popularity using audio features. Before we get into more detail, let me introduce my team. So my team starts with myself, Jill Faldu. I'm a TripleTen graduate, followed by Asok. He's a TripleTen DS graduate too. And then at the end, Preeti, she is a DS student. So Spotify gives every track a popularity score from 0 to 100. Predicting that score isn't simple since it depends on many audio features like energy, danceability, and loudness. Our goal was to build a PyTorch deep learning model that can predict popularity using just those audio features. Along the way, we created a flexible workflow with feature processing, tuning, and performance checks. In the end, we built a reproducible notebook with a tuned model, clear insights, and a baseline comparison. Now that we have shared our project goal, the next step was to frame it around the big questions we wanted to answer. So one question we asked was which audio features really matter for predicting popularity? Is it things like danceability, energy, loudness? Another key question was about the model itself. What kind of neural network architecture and hyperparameters would give us the best results? And finally, we wanted to know how well does our model generalize? In other words, can it make accurate predictions for new songs it hasn't seen before? Of course, before building any model, we needed to understand what data we were working with. That brings us to our data set. We use Kaggle's Ultimate Spotify Tracks database, which have over 230,000 songs. Our target variable was Spotify's popularity score, which ranges from 0 to 100. The dataset included 17 features in total, a mix of audio attributes like energy, danceability, and metadata such as genre, artist, and duration. Once we understood the dataset, the next step was cleaning and exploring it to make sure it was ready for modeling. We first checked for duplicate tracks and found none. There were only one missing value, so we end up dropping the row. Next, we looked at correlations between popularity and the audio features to see which ones might be predictive. Finally, we investigated multicolority to make sure features weren't too highly correlated with each other. Now my team member Preeti will go over data features.
Thank you, Jill. Hello, everyone. I am Preeti, a data science student at TripleTen, and I'll be walking you through the data preprocessing and feature engineering part of our project. So, as Jill explained about the data set, after getting it, we noticed it had wide variety of audio features that is used to predict this song's popularity. Some of the features were quite intuitive, then others, like valence, measures the positivity of a track, energy measures, like it will score high when the track is fast and noisy and loud. And speechness scores high for the words, for the tracks which has a lot of spoken words. So, after this, to better understand the relationship between the features, we created a correlation heat map. And this helped us to understand that some features like energy, danceability, and loudness were strongly correlated. However, since the correlation was below our threshold, that is zero point 0.9, we decided not to remove these features. Next, for the feature engineering thing, our goal was to keep the model simple while avoiding the irrelevant data. So we made several decisions. Um, we removed the identifiers like track ID, track name, and artist name since they don't add any like predictive value, and it could cause data leakage in the prediction. Next, we applied log transformation in the duration millisecond column to reduce the skewness. Also, we converted time signature into binary feature to reduce dimensionality. We dropped high cardinality categorical features like key and genre, which could have complicated the feature space without adding much value. After feature engineering, we analyzed how these features are correlated with the target variable, that is popularity score. And we found out that the features like loudness, energy, and danceability were positively correlated with the popularity score, meaning that popular songs tend to be louder and more energetic. On the other hand, acousticsness and liveness showed related negative correlation with the popularity score, means the less popular songs tend to be more acoustic or live performances. And next, we summarized this into a model execution flowchart to show the pipeline from pre-processing to the modeling. So this modeling part will be explained by my teammate Ashok.
Thank you, Preeti. So here we first created the model. We first load and pre-process the data. Then we split the data into three parts, and we scale the continuous features, and we convert the data into pytorch tensor, and we apply the hyperparameter search. Here we just tried 25 random configuration in order to save time. And we trained the model with early stopping and we record the validation root mean square error. And out of that, we select the best configuration that gave the lowest validation RMSE. And then we rebuild the model. And finally, we calculated the root mean square of test data. And we compare that root mean square error with the baseline. Next slide. So the best neural network design and hyperparameters in this model were like this. For the best architecture, 3 hidden layers, 64, 32, and 16 neurons, optimizer RMS prop, learning rate 0.001, dropout none. And so with this combination, our validation root mean square error was 14.3961, whereas for test RMSE, it was 14.4734. So it's lower than our baseline or sanity check, which was 18.2286. So we can conclude that our model is working fine. Next slide. So this is the learning curve. So on x-axis, we have epoch, and on the y-axis, we have a loss. So for both training and validation data, the loss is gradually decreasing. For training, it seems the loss is still decreasing, but for validation, it kind of plateaued at around 45, although we can see a little spike there. So overall, we can say that our model is working fine and there is no overfitting. So for future improvement, what we can do is we can apply advanced feature engineering in order to get more signals from the features. We can also broaden our hyperparameter search. We can also try incorporating textual data by NLP, and we can also reconsider including features like genre and key in this model. We avoided that in order to avoid high cardinality. And the conclusion part, Jill will do it. Next.
So for conclusion, our model outperformed the baseline mean predictor. We excluded the artist name genre we excluded artist name to prevent data leakage. Neural network was tuned using randomized search and early stopping. Results are robust and reproducible, enabling future enhancement. And we gained strong hands-on experience with pytorch despite it being our first time. We also tried to get data set using API from the Spotify, but we got some errors and we were not able to complete it. So it was kind of a good experience to understand how API Spotify works. And thank you.
All right, great job. So this was our first time using the PyTorch in one of our code puttings, but it's also first time using PyTorch for a lot of our students tonight. So, all right, team, what did you guys feel like using PyTorch? How'd it go?
I'll start. It went well, but as like I remember the dashboard project, like dashboard code jam, where I didn't know anything about Plotly, and then when I started using it, and then when something works, and then I get the result, I get so excited and happy that I finally found out. That's how it was for this project when I was working with API, like the bonus question. Unfortunately, we were not able to complete that, but I kept trying and trying, and then one point I kind of did the first 2-3 codes worked, and I got happy. But then the main focus of the project, like the bonus question, was to look for the own data set using the API Spotify, which we were not able to achieve. So yeah, I am still going to try after this code jam because I'm really keen to find out how it works. So PyTorch really made me feel excited and then kind of teach me like a new side of data scientist.
Yeah,
And
that's
also,
a really great point. Go ahead,
so
Shuk.
also because we know a little bit about TensorFlow, a lot of the concept can be translated into this PyTorch. So that was really helpful as well.
And the TensorFlow, can you maybe give us a short understanding for that? Because when I hear TensorFlow, I think of like lo-fi beats going with the flow, like, the turtle in the movie with the fish just kind of cruising. That's probably not what you mean.
Yeah. So TensorFlow is basically like a blueprint. It's very easy, less amount of code. Whereas PyTorch, there's it's like a more about Python, like lots of codes. Yeah.
So they're kind of different formats
Yeah.
for how to approach it, different
Yeah.
architecture, different structure there. Very cool. Preeti,
Okay.
how did it go for you?
It was really good for me, like being in a good team. So I learned a lot from the
Good.
team members. And yes, I use documentation a lot, like PyTorch documentation for implementing the stuff. So I got to know everything is there in the document. I just have to go through it and implement it.
Yeah.
It was really nice experience for me.
Yeah. That's like my favorite developer joke. Did you read the documentation? No, nobody ever reads the documentation.
Just the
No.
code part we took and then tried, okay, this is working like that.
Oh, I'm so glad. Okay. Did you have any moments that you guys felt like if you had just a couple of extra days? I mean, it sounds like the bonus question because you guys got so close, you guys were even attempting the bonus, but was there anything like if you had just a couple extra days?
Yes, that's the bonus question. Like I woke up today at like 3 to hope that I'll get the bonus question done. I worked yesterday too, but then I couldn't get it, but I really wanted to complete this bonus question. So so that I have like something to work on API related, because before there were projects where we were working on API, but I never worked. So I was really excited to work this time. Like last time I was with Ken and he ended up completing API, kind of the part of side of that project. So this time I was really open and I kept asking questions to him. And then right now too, I'm really open for that. So that is the one thing I really want to learn even after Code Jam. I'm excited to kind of figure it out. How do I do that stuff? How do I do the bonus question?
Ooh, really good follow-up. Feels like you guys can have like a nice little like inter-team session about that. All right. Well, that is our first team of the evening, Torch Quest, and that is Jeel Fidoo, Preeti Sagar, Ashok Mahajan, Mahajan. Yeah, there we go. Okay, good. And then William Mazzeo. Getting better. All right, here we go. All right, so that was our first team. Let's go on to our second team. Thank you so much, Torch Quest. All right, our second team of the evening is the Model Citizens, and this is Rawa Youssef, Jatan Bhatt, Eric McDougall, and Tirso Paneke. All right, Model Citizens.
Okay, just sharing my screen here.
Hello, our project is for Spotify. Next. So we are the Model Citizen team, and we are Eric, Jatan, Terzo, and myself, Rawa. Eric, he was the one that he has some experience with PyTorch, so we were lucky to have him. And he worked with the EDA. Then Jatan and Terzo, they worked about the model training and they prepared it. Then myself, I worked on documenting everything and doing the presentation. Next. So if we look here, this is our team, the Model Citizen. Remember us and vote for us if you need, and start to talk about what you need to hear from us if we need to improve anything. So we'll start to say music streaming platforms generate massive amount of data every day, from tempo and energy levels to danceability and balance. But can these audio features actually predict how popular a song will be? This project would explore that question by building and training a natural network in PyTorch to estimate a track popularity scores from 0 to 100 using features from the Spotify tracks database. By the end of this project, we aim to demonstrate the training and prediction ability to a deep learning model, evaluate its performance and regression metrics like RMSE and MEE, provide insights from experimentation with different architecture and hypermeters. Next, please. Why this matters? Understanding what makes a song popular has a real-world application for artists and producers, like guiding creative decisions, streaming platforms, improving recommendation engines, music marketing, forecasting hits, and optimizing promotion. From here, we will go with my coworker, Eric. He will explain what the steps that he did to work with PyTorch and what did he do with the EDA.
Google handled the exploratory data analysis for this project. We're looking, for instance, right now at a correlation matrix between the various numerical fields of the data set we were working on. So I handled much of the plotting that gave us insight into our data set and prepared us for machine learning pre-processing and machine learning modeling down the line. So in addition to that, we see a player plot, which unfortunately did not tell us much information, but is always like worth a try. And box plots that show us the overall distribution for how well something stood within just the interquartile range of these plots. With box plots, I created a subsection for anomaly detection. Using things like Nearest Neighbors, isolation forest, and interquartile range to see if filtering out anomalies gave us better performance metrics on our various models. In addition to this, I have some experience with previous notebooks with previous PyTorch models. So I took an old notebook and I filled it with Markdown and used it as a means to help educate my team members as to what the PyTorch model looks like and the various steps that are needed for creating one. I cannot claim to have written all that, but I did my best to kind of put us in a good place for the machine learning preprocessing that is so very vital for PyTorch and the machine learning modeling overall.
So that was Eric. He wasn't able to make it here today, but he explained the EDA section of it, and I was able to use pretty much everything he did for our data machine learning models. So I started with the pre-processing step, and for pre-processing, we pretty much defined the target as the popularity, and the features were the numeric columns as identified and highlighted by Eric in the EDA. I added in a robust scaler instead of a min-max scaler just to account for outliers, and then split the data set into 80, 10, 10. So 80% training, 10% test set, and 10% validation set. For the data preparation, so PyTorch requires tensors rather than arrays. So we had to convert the target and the features to PyTorch tensors, and we did this using a custom class called custom numeric dataset. Then we created the datasets to allow PyTorch to access the data and pass these datasets through data loaders. So it pretty much feeds the data to the model in batches, and we chose a batch size of 64. Then for the actual model building part of it, we started with a baseline model. It's just a simple neural network model using just one hidden layer of 64 neurons. And it applies ReLU to account for nonlinearity. And then we also created additional models for model experimentation. So the second model uses 2 hidden layers, and the third model uses 3 hidden layers, where each hidden layer basically adds more model complexity and allows the model to build more patterns. However, the downside of it is that you do risk overfitting. So with the third model where we have 3 hidden layers, we did add in a dropout. And then a fourth model we added, it's not shown here, but it basically was 2 layers, and it's a batch normalization to normalize each batch in to normalize each layer in batches. And this basically makes the model train faster and more stable, and it still retains the integrity of the model. And then we train the models through these loops to iterate over epochs, and we chose 10 epochs. So basically, each epoch allows the model to improve gradually, one at a time, one layer at a time. And this is great for tracking. So you can track the model performance in the data, and then we evaluate the models on the validation set using the loss function. Tirso, my other colleague, he's going to talk about the results that we achieved from these 4 models.
As you can see, the lowest scoring model was the MLP with 1 layer that scored 230 of MSRE. The best scoring one was the MLP with 2 layers and batch normalization. That one scored 212. Next. In here you can see predicted popularity versus the actual popularity of our base model. There was a little typo on the title. It was supposed to be the MLP with 2 layers and batch normalization, but it's pretty much the same chart. Next. On our exploratory findings, we found that popularities were widely unbalanced. Most tracks fell between 40 and 60. Possible correlations with the popularity were the loudness, the danceability, the energy, and the negative correlations that we found were the acousticness, instrumentalness, and speciesness. We also detected outliers in duration and loudness, revealing wide variability in the track structure. For the model development, we built and tested various MLP architectures in PyTorch. Layers, dropout, and batch normalization combinations were explored. The best model was the MLP with 2 layers and batch normalization that achieved an MSE of 212 on the test data. Regularization and normalization significantly improved model performance and generalization. Next.
So at the last, we are, as data science, we put our recommendation to improve this work or what we see from our perspective to make it better. So the first one was enhanced data integration. Integrate user engagement data like skips, playlist ads, or listening duration and social trends signal to strengthen prediction accuracy and identify hits earlier. Support artists with insights. Provide artists dashboards showing how this characterizes influence track success, guidance, a creative and productive decision. Personalized user experience. Diversity recommendations by balancing high potential tracks with mainstream hits, ensuring users are exposed to both safe bets and upcoming talent. Marketing and promotion strategy. Allocate promotional budget to tracks where models like BL, Player 2, Patch Norm predict strong potential, but current visibility is low. Data quality and future expansion. Improve data pipelines by handling secret features, filtering extreme outliers, and capturing richer descriptor like lyric sentiment, production style, and collaboration. Next. From this point, we can say that we finished our project, and we want just to make you remember, if you like what we did, vote for us. If you see that we need to improve, just put comments and tell us what we need to work. Thank you so much.
All right, model citizens. I love all of the graphics you guys use, some really great ones. We've got a few questions from our YouTube live chat for you guys. The first question being, why did you guys use a batch size of 64?
I think that was sort of a standard. I first tried with 32, 50, and then I ended up with 64. And it just, with the numbers that we, while we were training the model and then looking at the results, it just kind of looked the best.
In terms of like the results having a larger sample size to pull from?
Yeah, in terms of the loss function, the values look better.
Cool.
And
All right,
this,
next question. Ooh, hold on. The next question is how many generations in each epoch?
I don't know the answer to that question. I want to
Me
say
neither.
What does it mean?
100,000.
I'm gonna guess at least a grandma, a grandpa, maybe a great grandma, and a grandpa. An epoch's a long time.
That's a good
So I'm,
point that we can take it to improve in our work for the project. So we can make more analyze about this point.
yeah, I think it's a really good question because it's definitely enlightening me to like, I did not know that was a question. I will look that up. All right, last question is that what about vamping? Songs that move between both. So specifically related to kind of the takeaway around like acoustic songs are less energetic and less popular, louder songs are more energetic and more popular. What about songs that maybe move in between? Did you guys have any outliers like that in your data set?
Now, I think we mentioned that in the result that it's from 40 to 60. So we have something in between.
Did it and that one just kind of landed in the middle, yeah?
Yep.
Fantastic. Okay. So great questions from the live chat. Definitely one I'm going to have to research. But beyond that, beyond my own researching, how did it go for you guys working as a team? Because you guys haven't worked together before this code putting. Is that correct?
Yeah, that's correct.
So
Uh,
how did it go? And I think Jatan, it's your first time out the gate, yeah?
it is. It was the first code putting, and it was pretty exciting. I think I had a really good experience out of it. It was sometimes it's tough when everyone's working full-time jobs and have other, priorities to find the time. So we pretty much were doing like, 10, 11 p.m. onwards, and we were in like two different time zones, so that kind of makes it a little difficult. But we
Sure.
found a way to get everyone together and get the project done.
Fantastic. And Tirso and Rawa, this is not your first time out the gate. How was this one? Because this code putting was way different using PyTorch versus a lot of the other systems that you guys have used.
Yeah, so I mentioned that Eric had some experience. We were so lucky about it. Even he put in the GitHub the steps that how we can deal about it or what we need to do as steps. And the second thing, I think this time for me, it was like not just scaling myself more, but it was like I need to adapt to be this data science that he doesn't fight for rules. And I started to take step back and give that chance for the others. And I was like, oh, whatever left I can do. So it helped me to improve my mindset to be adapting with, I don't want to be this one that it's always cracking and doing noise. And I want to be in this environment that I start to grow up and look at it as a scientific way. So I think this is my best time for the project, that I felt that I'm more calm. I'm not too worried. I feel that it's the best one. I don't know why. And for somehow most of my project, I'm the only woman between all of the guys. So when I came, I'm like, oh no, it made me remember the dudes. So I was worried at the beginning because, it's a different language between us, but they were really nice. And I had a lot of work, so I was coming late and they were giving me, oh, we did 1, 2, 3, and we are just stopping there. And this is my first time that they used Google Lab. So we could see actually everyone working there and editing something. So it was amazing
That's
for
real
me
nice. Yeah.
because I could see every step that everyone was working on it. Because the before code jams, when we were working separately. Then we merged the data together. But this time I could see each improving that they are doing for the codes. And when I was wondering why this happens, when they edit it, I can understand the process of it. So it was
So
great.
a nice tool there to help out.
Yeah.
Fantastic. All right. So that is the model citizens with Rawa Youssef, Jatan Bat, Eric McDougall, and Tirso Peneke. Thank you so much. And it seems like you guys got a vote. Yep, a vote in the live chat also. So yay. Remember that you guys can vote in the live chat for our teams. All right, our last team of the evening is the Beat Predictors, and that team is Ken Klabnik, Victor Klufinski, Janina Babu, and Mo Wyman.
All right, how's it going?
Oh, we're good.
Let me get our presentation pulled up here. I'm going to move my Zoom window to this monitor over here, so if I'm looking in a weird direction, that's my bad. So I will go ahead and share my screen now. This screen. There we go. So, point of order, Victor submitted a recording. I believe you have that, Tiffany.
I do.
And that'll be at the start of the presentation. But let me cover these first couple slides first. Hello, we are Team Beat Predictors. And like the rest of our competition, we're using some deep learning techniques with PyTorch to predict Spotify song popularity. Our team consists of myself. I'm Ken Klabnik. I'm a data science grad. We have Janita Babu, who is also a data science grad, of course. Mo Wyman was unable to participate. He ran into some stuff, and so he sends his best. And then, of course, we also have Victor Klufinski, who is a data science student who is graduating very soon. And so, Tiffany, are you able to play the audio while I'm presenting? Or am I going to have to pass this over to you?
I believe you'll have to pass it over to me.
Sure. Let me stop sharing a little bit.
Yeah.
Yep, go ahead.
Here we go. Here is Victor.
Models to predict Spotify song popularity using
Hold on,
audio
Victor,
features.
Victor, slow down, buddy. You gotta start from the beginning, Victor. Gosh, he's always such in a rush.
Hi everyone, I'm gonna tell you today about my part that was focused on exploring data collection and preparation. So we built models to predict Spotify song popularity using audio features. And we used PyTorch for deep learning, compared multiple models, and evaluated them with regression metrics. Here we cleaned the data, applied scaling and encoding, then we converted it to PyTorch tensors with data loader and creating like a ready to train data set. So for the EDA section, I focused on exploring how different features in the data set relate to popularity. And first I checked for missing values and duplicates and found only one missing track name and a number of duplicate track IDs, which were removed to clean the data. Then I generated a correlation heat map, which is highlighted the features like energy, loudness were strongly correlated, while others such as speechness and acousticness showed weaker relationships with popularity. I also looked at the distribution of genres where a few categories dominated the dataset showing imbalance. And finally, I analyzed popularity distributions, which has helped to understand which genres the model predicts more accurately. And this EDA step gave us a clear view of the dataset's strengths and weaknesses before training. Thank you.
All right, Victor, if you're catching this later, thank you very much. And we'll go back to the presentation here. Yes. So Janina, did you want to speak about the models?
Yeah, definitely. Hi, I am Janina. TripleTen graduate. Victor walked us through the data preparation and EDA part. So our dataset is now ready for model training. I will now discuss the different models we explored and the approach that we used to evaluate the performance. As a starting point, we implemented a linear regression model to serve as the baseline for comparison. Next, we built a basic feed-forward neural network. Here you can see the workflow, which includes one hidden layer with 32 neurons, which is followed by linear activation, ReLU activation, and the output layer. There is only one hidden layer in this model. And this structure is simple but effective in capturing the non-linear relationships in the data. Next slide.
There it goes.
Okay. Then we move to a deeper feed-forward network, which is designed to learn more complex patterns. Here you can see the workflow. There are 3 hidden layers. Start with a layer of 128 neurons, followed by the activation. The second hidden layer with 64 neurons, followed by the activation. And the third hidden layer with 32 neurons, followed by the activation, and the final output layer. We also developed a variant called popularity predictor. Its architecture is similar to deep NN, but it gives manual control over the forward pass, which is useful if we want to customize it later by adding the features like batch normalization. After that, we implemented a version of network with dropout layers to prevent overfitting. Here you can see we start with 128 neurons, followed by the activation and dropout layer. Then the second hidden layer with 64 neurons and the dropout activation and dropout layer, and the final output layer. So we set the dropout rate to 0.3, which means that 30% of the neurons are randomly turned off during the training process, which helps to improve the generalization. We also explored the variant of this method to which gives the manual control over forward pass. And finally, we trained our data using an inbuilt model, which is called TabNet regressor, which is specifically for tabular data. Next slide. So now all the models are defined. So our next step was to train and evaluate them. So to ensure a fair comparison between each models, we use the same condition. We use the mean square error as our loss function. And for optimization, we used Adam optimizer with a learning rate of 0.001, which provides a good balance between the convergence speed and stability. And the training was done over a maximum of 100 epochs, but we used early stopping technique to prevent overfitting. And the pytorch data loader is used to handle the batching efficiently during the training. After training, we evaluated each model's mean square error, root mean squared error, and mean absolute error. Now I will hand it over to Ken, who will explain the results and insights that we have gained through this project. Thank you.
Thanks, Janita. So the results on your screen is a whole lot of numbers. Don't worry, I'm not going to read them all off to you. But the main takeaway is that TabNet had the most success out of all of our models. The simple neural network, the simplest architecture there was, also came very, very close to it on mean squared error, which is the metric that we're testing on. However, it also took the longest to converge. It is the only model that used all 100 of the epochs that we limited ourselves to. Gina implemented a patience function to try to prevent overfitting. So some additional comments. For the linear regression, which was sort of our baseline model, it was implemented as a neural network, but it is extremely simple and it's a linear regression. And it did underperform the other models, which does indicate that there is not a linear relationship between the data. As well as we had two pairs of models that had very comparable architecture to each other and were just slightly different implementations. And those two pairs of models performed similarly to each other, enough so that I'm comfortable just saying it was a little bit of randomness in the training that caused any differentiation. And so for additional ways that this project could be expanded, we could look for additional audio features or features in the metadata. We could account for the popularity of individual artists or the lyrics for music that has lyrics. We could even do k-means clustering to determine songs that are similar to each other with that algorithm, and then try to correlate that to popularity. Obviously, there are always going to be more neural network techniques and architectures to play through. It's a space that is constantly expanding. And of course, it would be nice to be able to deploy this to a web app or dashboard for your viewing excitement. But that's all things that could have been done if we had chosen to expand on the project more. And with that, I believe that covers everything we've got for you. Do you have any questions?
All right. Great job, guys. You guys have lots of votes in the live chat. And the general consensus seems to be that your presentation was real tight. You guys had a lot of really clear metrics in there. So let's talk about those metrics. You guys talked a lot about errors. Now, I'm a developer. So when you talk about errors, that feels like a bad thing. But here it feels like this is something that is useful information to you. So maybe you can help all of us understand how all of these different types of errors are useful for you guys as data scientists.
Yes, Janita, do you want to take that or should I? I'm fine either way.
You can proceed.
Okay. So when you have pretty much any real world data, there is always going to be some amount of randomness or noise to it. It is impossible to be 100% right about everything 100% of the time in statistics. That's just not how it works. And so error is the metric that tells you how far off you were from the correct answer. So of course, when we're doing anything with machine learning, we have a separate training set and we have validation and test sets. We use the training set and we have the model try to predict that, and it will get a certain amount of error and it'll know how far off it is, and eventually it will settle on something. And so with a neural network, we have that architecture that we've seen. There are simpler ones as well. And then you use validation and test sets to determine how good it actually is based on data that it was not trained on. You specifically want to withhold some of the data for that. And so the specific metrics that we have, mean absolute error over here on the right is the easiest one to explain because it's just the average of all the errors it took on every prediction it made. And so the thing about
So
that
the
one,
lower the number, the better.
yes, all three of these metrics are you want lower ones because that is smaller errors. And so with mean absolute error, it treats the data the same whether that error is spread out equally with all the predictions. Excuse me, water. It treats it the same whether it is spread out across all predictions or whether most of the error was lopsided, like it got certain things very wrong. So if you want to sort of punish it a little more for specific predictions that are way out of whack, you use mean squared error, which is sort of the same idea, except for you take the squares of all the errors. You multiply them by themselves, and that sort of stretches out the bigger ones to be disproportionately big. However, that also gives you a large number that is a little bit hard to interpret, which is why root mean squared error exists. It's just the square root of the mean squared error. And that sort of brings it down to a comparable range to where the mean average error is.
Okay, so you can see those numbers like a lot more closely aligned together.
Yes.
Yes. Okay.
Mean absolute error is literally just how far off you were on average. So
okay.
And then the
so
other two are just a little bit more
not terrible
sophisticated.
in some of them. Those are all pretty consistent. That's good.
Yeah. We got remarkably close.
Fantastic. Really great job. Now, Janina, this was your first time. I know that Ken and Victor are grads. How did you enjoy
my second time?
It's your second time?
Second time.
Oh my gosh, time has flown for me. Oh my gosh, it's all just all the months and back to school. Okay, so Janina, how did you feel like it went this time versus your first time? Do you feel like I know PyTorch is different than a lot of the stuff, but in terms of the overall process and the speed, you guys only had 5 days. Did you feel like it went more smoothly?
First of all, the PyTorch is totally new to us and we don't have any idea about it. So we just do some researches and first we define what is this class means, how we can define it. When we started with one layer, then we think about if there is 2 layer, what will happen? And if it is 3 layer, what will happen? There are so many parameters we are added again and again after each session. And when we first run our code, one of us like, oh, I run it for 5,000 epochs. And I was like, I run it for 100 epochs. So how we can fix that? So it's totally something like, oh, did anyone get with 100 epochs or 50 epochs the best result, something like that? And we will discuss it. And after applying his hypertuning parameters, finally we got our best results with less than 100 epochs.
Yeah, I can see that here. And then on this, you're able to identify which one's the best epoch out of all of them for that model. So that's pretty rad that you guys were able to kind of pull that data out and show like which one is the best one for this specific model. Really cool.
Yeah. And in terms of speed, TACnet is a not good one because it takes about 15 minutes to run for the 39 epochs, but all other are quick responding. So in terms of speed or functionality, we can decide which model we should select.
So not running 400 epochs is the way to go. Yeah, definitely not.
Yeah.
We'll need to add a few days. Fantastic. All right. So that is our last team of the evening. Thank you guys so much. That is the beat predictors. You guys have lots of really wonderful comments and votes in the live chat. So make sure you check out those. And thank you guys so much for voting for our teams. That is Ken Klabnik, Victor Kiflinsky, and Janina Babu. So let's go ahead and just remind everybody that if you, since we've had all 3 of our teams tonight, so please make sure you get your votes in. If you're a student of ours, you can vote for your favorite team in the hub. We have Torch Quest, the Model Citizens, and Beat Predictors. And then if you're not a student of ours just yet, you can vote in the live chat. And thank you so much for doing that. I see so many of you, Alex and Ming and Sebastian. Wonderful to see you guys voting. Thank you. That is all from us tonight at TripleTen. Over the course of the next week, our judges are going to evaluate the projects and presentation for our teams, and all of our results will be announced by August 27th, and that includes audience favorite, and they get a special prize. Hopefully, it is not a piece of cheese from my cat Sharkbait, although he is in a cheese era right now, so we'll see how it goes. All right, I want to say
perhaps a cheese epoch.
It's a cheese epoch. Yes, he would like 400 of them also. All right, I want to say a special thanks to all of my team members who help get this project going every week. That would be, let's see, Daniel, Camilo, Alyssa, Elena, Olivia, Dennis, Anastasia, and of course, Sharkbait. Thank you again for all of you taking the time. I mean, we've had people tonight that are students of ours talk about how they're working full-time jobs, their parents, they've got lives, right? We've had students tonight on teams that are joining from work, they're joining from their car. Like the hustle is real for you guys. And I appreciate you guys taking the time and finding the time to work together and really just grow yourself and challenge yourselves with this new PyTorch neural network. Sounds so impressive. I'm so glad you guys got an experience like that. All right, my name is Tiffany Hall. You can find me at Tiffany Codes on Instagram, and you could probably find Sharkbait putting the hyper in his hyperthyroidism. Thanks, you guys, for watching. Enjoy your evening, and we'll